This data was taken from Engineering Toolbox website, and I took the experimental densities for a number of gases and then converted them into volume in liters under standard conditions and 1 mole. There is a pattern roaming around there. But let's come back to this. Let's set this aside. What we're going to do is calculate the volume in liters of an ideal gas under standard conditions and 1 mole. There are standard conditions. If you see temperature in Celsius and you're doing a gas law problem, automatically convert that thing to Kelvin. And since it's molar volume, that means the volume of 1 mole. So we're assuming 1 mole. Now, how to solve this? Is this a combined gas law, or something to do with pressure, volume, and temperature changing? And if you look at the information, nothing's changing. And you're given the amount of gas in moles. That means we need to use the ideal gas constant, R. Now I use these 3 values, so let's pick the one that has the easiest pressure units with which to work. And since I give these 3 values of R to my students, I'm going to pick the value of R that has atmospheres in it. Now, if we're using the ideal gas constant, that means we need the ideal gas law. Or do we? I'm going to solve this problem first using the ideal gas law, PV equals nRT, and then I'm going to solve it a different way. First, this way. We're calculating volume, so we need to solve our gas law for volume. Now we need to plug everything in. Take the number of moles of gas that was given, multiply by R, multiply by the temperature, divide by the pressure. Do our unit check. Moles, good, they cancel. Kelvin, cancel. Atmospheres, cancel. And if we multiply everything out, we get this. For significant figures, there are 5, and this is a different problem because of the way the information was given. The standard conditions for temperature and pressure are assumed to be exact. So we have an infinite number of significant figures in those. We're given exactly 1 mole, because that's what molar volume means. That means that the significant figures are actually coming from the value of R, which is unexpected. Normally at this level, you don't worry about how many significant figures you have in R, as long as you have enough. And that's why in all 3 of those values I give for R, they all have at least 5 significant figures in them. They actually go out more digits. But there's some uncertainty that starts pretty soon in most of those. So 5 significant figures is enough for anything I'm going to do. Which means our answer gets 5 significant figures, 22.414 liters. Now, I like the ideal gas law. Mathematically manipulating it's not really an issue for me, but we're not talking about me, we're talking about you. Can you mathematically manipulate that formula in a short period of time and be sure of what you're doing? Because see, that answer, I don't have a good common sense check for that answer. It could have been 25, 50, 95, 3 liters, and least at first glance, I wouldn't know whether it's reasonable. So you need to find a way that allows you to work the problem efficiently and check your work easily. Do your unit check. There's also the problem with unit transformations. What if you're working with volume and it's milliliters? The gas constants have liters in them. What if you're working with mass, or density, or molar mass? It's not easy to use the ideal gas law under those situations. So let me show you the other way. This is actually the way I prefer now to work these problems. And this is the way that I'm going to work the rest of the ideal gas law problems in my podcasts. I give constants out. Therefore, you've got the value of R. So let's use that to our advantage. If you have the value of R, then start with the value of R and multiply and divide until your units work out. I always recommend that when you write the value of R out, you don't write it the way I wrote those three initially. It's not that it's wrong. It's just by putting the units at the end, and since they're combination units, it can be a little difficult to work with them. So notice what I've done down below. I've clearly distributed the units for the numerator and denominator. And it makes it easy to check units. It also makes it easy when you need to take the reciprocal, when you divide by R. If you think of R, as a way to relate pressure and volume and moles and Kelvin to each other, you think of it as a conversion. Remember, we can take the conversion the way it's written, or take the reciprocal. And the way we determine which way we want to use it is by going back, looking at the problem, and seeing what's being asked for. And we want the volume in liters. We want liters. So look down below. When we're done, what do we want? Do we want liters in the numerator or liters in the denominator? When we're done, we want liters, not reciprocal liter units. So we're going to start with the value of R this way. Now R is not a mathematical formula. R is shows the relationship between pressure, volume, N, and temperature. So we multiply and divide to make our units work. We're given 1 mole, multiply by 1 mole, so the units cancel. We're given the temperature, multiply by the temperature to make the units cancel. We're given the pressure, divide by the pressure to make the units cancel. And look at another advantage. By writing it this way, it makes it easier to see the numerator and denominator in all the pieces. I think it makes it easier to multiply. Now the PV equals nRT is buried in here. Remember, we were looking for V. So V equals nRT divided by P. So volume, 22.414 liters, equals N, 1 mole, times R, times T, divided by P. It's all right there. The advantage, which you'll see later too, to doing it this way is if you need to do some unit conversions, you can throw those in there and just keep adding pieces onto this puzzle until you get the right units. Now, that data I showed you in the beginning, let's look at that. We calculated the standard molar volume for an ideal gas to be 22.414 liters. Now, these are actual experimental results, and I would argue for the ones that I've highlighted, those are pretty darn close to ideal values. The ones I highlighted all have standard molar volume of 22.4 liters. So one thing this shows is that under some conditions, the ideal approximation for gases is not a bad one. It works for this. As long as you don't take the temperature too low or the pressure too high, it's not a bad approximation for many gases. Sure, I look there and see, butane, sulfur dioxide. You've got really high and a really low value there. Well, that just means that those don't behave as ideal gases. But the ones I highlighted seem to approximate the 22.4 liters, seem to behave like an ideal gas.